Thank you very much. So first of all, I would like to thank the organizers for putting up this very nice conference and for inviting me here to present my work. My name is Andrea Bergschneider and I'm a senior scientist in the group of Michael Köhl in Bonn. And today I want to show you experiments on two different experimental platforms. And first I want to talk about ultra-cold Fermi gases and more specifically about strong correlations. And as this is a few body conference, I want to show you a few body experiments that we did, but then move over to a many body platform. And then in the second part of my talk, I want to completely switch gears and introduce you to the atomically thin semiconductor platform, where we had done measurements on polaron physics. So strongly correlated systems or strong correlations arise from the interplay between kinetic and interaction energy, and this leads to a rich phase diagram, and it's thought of being one of the hottest candidates to explain high TC superconductivity. And the Fermi Hubbard model is in some sense the simplest model that you can think of that has this interplay between the kinetic and the interaction energy. And although this model seems to be very easy, very simple, it's not easy to solve. It's actually in some regimes it's not solved at all. And this is why there is a huge effort from theory, but also from the experimentalists to learn more about these systems, and that goes under the name of quantum simulation. So first of all, if you look at the most essence of this Fermi Hubbard model, so I personally like to think about it in like a very small kind of system, which is the fundamental building block. And this is simply two fermions that are on a double well potential with two different spins, and the particles can hop back and forth, and when they are on the same side, there is an on-site interaction. And the ground state of this object is a spin singlet state with antiferromagnetic correlations. And during my PhD in the group of Selim Joachim, we have already heard from Georg Brun about some experiments in this group. During my PhD, we were basically motivated to basically realize this building block and then expand the system further. So we were setting up an optical tweezer, a pair of optical tweezers that are partly overlapping to realize this potential and then load the fermions into it. And I want to quickly mention that meanwhile, there has been an expansion of such a system in the group of Wasim Bakr to 8 sites. So this tweezer array gives us, or these tweezers give us the possibility to have a lot of control on the system. And first of all, we were realizing an adiabatic preparation of this ground that I've already mentioned by basically first preparing two particles in one well, then switching on a second one, ramping the tilt to 0, and then ramping the interaction energy to arbitrary values that we were interested in. This is an adiabatic process. And on the other hand, we were working very hard on getting an imaging technique that gives us a single particle resolution and at the same time a spin resolution. And the interesting thing about this imaging technique is that we are not relying on any pinning lattice, as very often is the case in cold atoms, but we could just capture the fluorescence of the photons from the atoms. So this gave us the possibility to access the momentum space of the system. So we were preparing the ground state and then releasing the system in a large harmonic trap and wait for a quarter of a trap period. And thereby the initial momentum distribution gets mapped to the spatial distribution. And then we were just imaging like the two atoms that were in the system. And with this, we had the momentum information. And similarly, we could not directly resolve the double well in situ, but by doing a site selective kick and waiting for an optimized time, we could really tell the population in the left and the right well. So what does this give us now? It gives us basically an insight into two conjugate variables. And we wanted to use this in order to learn more about the system. So here are typical measurements here for for a non-interacting system, and here for a strongly repulsive system. And in the non-interacting system, one basically sees that all the four possibilities of both particles being at the left and at the right well, or one in the left and one in the right, are equally are realized with equal probability. And in momentum space, what happens is that both particles do a double slit experiment independently from each other, and we see this constructive interference in the center and the side fringes. Now, what happens if you switch the interaction on? Well, we get a conditional population in the real space, and in the momentum space, we see that there are two particle correlations building up, and we see this fringe pattern along the relative momenta. And what this tells us now is that there is not only an incoherent mixture, but in contrast, it is a coherent two-particle state, which has an antiferromagnetic correlation, and it's basically, that's the proof that this is really a spin singlet. So now we are there with our knowledge that there are correlations, but we were interested in extracting more information about this. And after thinking a bit about the system, we were trying to see whether we can, like, how much information can we get? Can we basically reconstruct the density matrix? And it turns out, yes, one can do this. So first of all, the real space information is just the population along the diagonals. And then it turns out, if you look at the momentum distribution, you can set up basis states that are the coherences and the correlations. And then by fitting these patterns, one can extract the prefactors, and these are just the off-diagonal entries in the density matrix. And even more than that, it turned out that with all this information that we got here, we could in the end certify the entanglement in the system. I mean, we all know that there is entanglement, but we could really give a proof on this. And in this context, the interesting question is now, could one find ways to expand this technique and do this for more particles and larger systems? How far can one push this limit? So that was sort of like the few body part. Now I want to sort of put a bit more particles in and sort of like switch location to the University of Bonn. When we look at this Fermi Hubbard model, I've told you that this is a hot candidate for superconductivity. However, if one looks at real superconductors, one sees that they are consisting of layers of these planes where the electrons can hop around, and they are weakly coupled. And so the question is that arises, like, what is the role of these couplings, and would this actually, for example, increase the critical temperature in the system? So we were interested in realizing sort of like the first step towards several coupled layers, which is the bilayer Fermi Hubbard model. And I have to maybe mention here that when I didn't yet join the group when they published this paper, but I still want to show you the results. So for this bilayer, one has now a third coupling term, which is the interlayer coupling. And we assume now that one can tune this independently of the other two parameters. So let's quickly have a look at what we would expect. So first of all, if the interlayer coupling is 0, we just recover the old phase diagram of the Fermi Hubbard model. And for half filling, this would be just an antiferromagnetic state. However, if we have a very strong interlayer coupling, much stronger than the intralayer coupling, then you can think of it as a 2D array of double wells. I've just shown you the double well, right? So there would be singlet correlations along these bonds here, and this is then described by a bilayer band insulator, and there is a quantum phase transition happening in between those. So we wanted to explore this system and especially look at this competition between the intra and the interlayer correlations. And this is how the experiment looks like. So we have potassium-40, so fermionic potassium-40 in an optical lattice. The X and the Y lattice are just two standing waves that give us the individual sites. And the lattice in the Z direction is a shallow angle lattice, such that when we also have interference fringes of the laser beam, but there are two different colors involved, and this gives us the possibility to form double wells now in the vertical direction. And we can control the coupling between two of these layers. So what we do is we load our atoms into one of these sort of like bilayer system, and we want to really control that we have a low entropy in the system. This is why we also shine in a repulsive barrier to really single out the center of the trap, where we can control the occupation probability. And we are interested in really loading 2 particles per side if I only think about one layer. So this means I start with the band insulator in one layer, and then we split it into 2. So we have really 1 particle per side. Okay, of course, with experimental imperfections. But this is our starting point for our experiments. And now we are interested in looking at the correlations. So we want to characterize the intralayer correlations, but we don't have single site resolution. However, we can measure the spin structure factor, which is the global quantity that characterizes the antiferromagnetic correlations, by a simple trick. We do a Ramsey technique. So imagine that you have the perfect antiferromagnet. Now we would apply a magnetic field gradient and flip all the spins into the plane, and then they would precess, and we wait until the perfect antiferromagnet would be turned into a completely polarized state. And then we measure and analyze the correlation, and with this value we basically get the staggered structure factor, and we compare this to the uniform structure factor when we did sort of like not do the whole sequence. And if this is larger, then we know, okay, there is antiferromagnetic correlations. So we did this experiment, and on this side we have the completely decoupled planes. On this side we have the strong interlayer coupling, and indeed we see that the staggered structure factor is initially very large. So there is a lot of antiferromagnetic correlations in the system, but it decreases eventually, meeting the uniform structure factor. So at this limit here, we have no antiferromagnetic correlations whatsoever in the system. So the question is now, where did they go? Did they just decohere, or are they really sitting along the vertical direction? And in order to look at this, we basically prepare our system, we freeze the double wells, and then we merge these double wells in the Z direction. And depending on whether we have a singlet state or a triplet state, we will end up in 2 different final states, which we could distinguish. And this is now the measure in order to extract the interlayer spin correlations. So the interlayer spin correlations are now these orange points, and indeed, while the intralayer correlation goes down, the correlation in between the wells, in between the layers, really increases. And so the correlations got really moved to the stronger coupling bond in the system. So these experiments are really just the starting point of exploring a lot of physics that is related to bilayers. As our experiment cannot decrease in temperature much further at the moment, we decided to look into different direction, namely to look at other competing coupling mechanisms by simply putting a superlattice along the along this X direction, and explore topological systems with interactions, or dynamically control these couplings and go towards Floquet driving. So this is currently the direction that we are working on. So with this, I'm sort of like set with talking about cold atoms. Now I want to completely switch gears and give you a flavor on a new experimental platform that had arisen recently, and that has a lot of interesting physics to be discovered. And this is the platform of atomically thin semiconductors. So these atomically thin semiconductors are van der Waals materials, and you probably know the most prominent candidate, which is graphene. And these van der Waals materials are layered materials with very weak force between the layers, and this allows one to isolate individual monolayers just by mechanical exfoliation, very simply with a Scotch tape. And these materials can have very different properties. There are insulators, there are metals, there are semiconductors or magnetic materials. And by stacking these materials now on top of each other, one can really design the like samples with tailor-made properties. And one material that I personally find particularly interesting is the family of transition metal dichalcogenide. So an effective monolayer here has transition metals in the center, like molybdenum or tungsten, and then chalcogenide, like selenium or sulfur, around it. And the interesting thing about this material is that it is, first of all, a semiconductor, but more importantly, if I only have a monolayer, it turns out that it has a direct band gap. So it is possible to put in optical excitations and explore quantum optics with semiconductors. So how is the physics working in these semiconductors? Well, here I basically show you the band diagram in a very simplistic way. We have the valence band and the conduction band. And in a semiconductor, usually when the temperatures are very low, the valence band is filled completely. The Fermi energy lies somewhere in between the band gap, and the conduction band is completely empty. So, but it turns out if one builds a structure like this, where one has this transition metal dichalcogenide separated by an insulator, which is usually hexagonal boron nitride, doesn't matter for now, and then there is some metal, like, for example, few layer graphene, and we apply a voltage between those two, what one can effectively do is one moves this band structure around with respect to the Fermi energy, and one can pull it down all the way to the moment where the Fermi energy lies within the conduction band, and then from the contact, electrons can tunnel onto this TMD. And this means that I can dope the system, I can tune this in complete contrast to what I can do in other semiconductors. So we have a control knob on the electron density in the system. And the second interesting ingredient here is now, as the maximum of this valence band and the minimum of the conduction band are at the same quasi-momentum, when I shine a photon onto this system, I can take an electron from the valence band and promote it up to the conduction band. And now I have this monolayer system, so the field lines between the electron being negatively charged and the hole being positively charged are not screened because there is no material around, right? So the Coulomb interaction is really strong. And so there is an exciton forming, a bound object between an electron and a hole. This is sort of like my optical excitation that I'm now interested in. So if one now varies this photon energy, what one finds is that when the photon energy is above the band gap, that there is just absorption happening. But when the photon energy is below the difference between the valence and the conduction band, there are these resonances, and these are precisely these exciton resonances. You can really think of this now as a bound two-particle object like a hydrogen atom. And this is a calculation of how this exciton looks like in real space. So here you see the lattice structure, and this exciton object is much larger than this lattice structure. And the Bohr radius is approximately 1 to 2 nanometers. I've already mentioned this strong binding energy, which is on the order of 200 MeV. The band gap is about 1.8. So this is a significant amount of sort of like this band gap here. And it has as a consequence that these excitons are having very large oscillator strength. So it's very probable that I can excite an exciton with a photon. And it is also very probable that this exciton decays very quickly again, just for the same reason. So the timescales of these excitons, the lifetimes of the excitons are in the few picosecond regime. So just as a reminder, what are now the main players in the game? There is the exciton, there are the electrons, and the densities we can vary, and I can get to minimum distances of about 5 nanometers. These systems are two-dimensional, and the temperature, when I cool it down to 4 Kelvin or lower, does not really play a role now in this physics here. And now I want to quickly remind you of what Georg has already talked about, namely that there is a bound state of 2 excitons existing, but I will not focus on this for today. I will focus on the trion being a bound state of an exciton and an electron, and the binding energy in molybdenum diselenide, which is my favorite TMD, is 25 millielectron volts, and the Bohr radius is 2 to 2.5 nanometers. So now, in contrast to the exciton, where I said it has a large oscillator strength, to excite this trion with a photon is not very probable, because now I'm relying on the fact that this trion forms somewhere where there is already an electron. So this localization really brings the probability down that I can excite this trion. So in a normal like spectroscopy measurement, I would not easily see this trion. So let's look at real data now for this reflection measurements. This is what one usually gets for a charge tunable device. So here we have the gate voltage and the energy of for the resonances. And between -4 and 0, there is the neutral regime. We have no electrons whatsoever, and there is this prominent exciton resonance. Now, if we increase the doping, there is a second branch emerging at an energy where we expect the trion, and it becomes brighter. And this is somehow now weird, because I've told you that the trion is very dark, but the explanation is simply that now when I have more electrons around, the trion can sort of be a superposition of different electrons being part of this trion. So the oscillator strength is expected to scale with kF squared, or linearly with the density of the electrons. Or you can see it from another angle. You can see it in the following way. There is an exciton in the system, and it attracts the electrons around it. And this is basically impurity physics going on. So also there, one would expect that there are 2 branches. For polaron physicists, this is called the repulsive polaron and the attractive polaron. So I've told you now some qualitative things. Let's look a bit more quantitatively, because we can try to extract information from the spectrum by, for example, fitting the radiative and the non-radiative line widths. And this is what one gets. So first of all, I normalize everything to the radiative line width of the exciton. And what we observe when we tune the gate voltage, and this is very preliminary data, what we see is that indeed this, what we could already see qualitatively, this line, the radiative decay, the radiative line width increases linearly and then sort of like levels off, while the radiative line width of the repulsive polaron indeed goes down. So there's this transfer in oscillator strength happening that one would expect for a polaron. And then, more importantly, the sum doesn't stay 1, which one would expect. And we can understand this in the following way. So what the electrons do to the exciton is they will try to screen the strong Coulomb interaction between the electron and the hole, and thereby reduce the binding energy. And when the binding energy is reduced, then the oscillator strength is also going down. So one would not expect that this is the same than it is for just the naked exciton. Yeah. So I have to say that this extraction is something very delicate to do, because there is a lot of input parameters going in. And that's why we wanted to do a second experiment, which is a dynamic experiment. So we wanted to, we excited the repulsive branch, and then the system can decay into the attractive branch. And we were resolving we did a time resolved measurement of the photons that are coming out of this attractive branch in order to check, is this decay really looking like what we see from the spectrum? So this is how data from this measurement look like. First of all, we have this very short peak, which is just the leakage of the excitation laser. It gives us a perfect zero, like where is time zero in our experiment. And then there is an increase and a decrease in the photon numbers. And this is something one would expect for a 3-level system that decays in 2 cascades, that there is a rise time and a fall time. And it also turns out that you cannot tell which of the times belongs to which of the decay processes. It's always the shorter time that will be the rise time and the longer time scale that will be the decay time. But what we can see very obviously is that when we change the electron density in the system, that the rise time changes while this decay time doesn't seem to not change at all. So we measured this for different electron densities, and we again found a linear increase in the calculated rate, which is in agreement with what we have seen from the spectrum. But then there are some discrepancies here for the higher electron densities, and we are currently about to understand where this is coming from. So what is, for example, the role of non-radiative decay in the system? How does this cascade exactly work? So that's where we at the moment are with our understanding. We have to study the system more. But before I conclude, I want to quickly show you another aspect, very interesting physics that one can do with these systems, and that are very related to what Georg has told us this morning. Namely, as this exciton is very bright and couples very nicely to light, it is a perfect candidate to be put into a cavity. And in these systems, one can make the mode volume so small that one can enter the strongly coupled regime. And that then simply looks like the following. You have the photon mode from the cavity and the exciton resonance. And they are coupling and forming new hybrid exciton photon states, which are called polaritons. And these polaritons can now be used in order to sort of do realize interacting photons, because the interaction part is being taken care by the exciton, by the matter component. And one can even push, or like maybe one can also push this to the limit where one can get into a photon blockade. So where one makes sure that there is only a single photon in the system and there cannot be 2 or more. What one can additionally add to the system to make it even more interesting is to again put in electrons. And we have already studied this, and what we observed is that in contrast to just polariton-polariton interaction, the electrons will enhance this interaction strength. And last but not least, the cavity also prolongs the lifetime of these polaritons. And so one can get a large population of these polaritons in the system and enter the regime where one can do Bose-Fermi mixtures. Yeah, so with this, I'm at the end of the second part of my talk. I hope I could give you a bit of a flavor on the TMDs and what kind of physics one can explore there. I think it's a very promising platform, and we will probably see many experiments coming up in the future on this. And I guess for all this interaction physics, it's also interesting to get input from experts on few body physics. And before I, this is really my last slide. So I want to thank all the teams that I've shown results from. First of all, the team of Selim Joachim, where I did the few body experiments during my PhD. Then the group of Michael Köhl, where from which I showed you the bilayer experiments. And last but not least, the polarons in the TMD that I've done in the group of Imamoglu in Zurich. Thank you for your attention.
Thank you very much for this nice talk. Now we have time for questions. Tobias, sí. Dorte is giving the microphone.
Okay, thank you for the nice talk. I'm curious about both the excitons and tryons. When you increase the Fermi energy, you have, I mean, because of Pauli blocking, at some point to destroy your exciton, first your exciton, then your tryon. Can you see that? I mean, I understand that you are interested in other kind of physics, but can you see this kind of mode transitions in your experiment?
So first of all, as I said, we can basically see that the binding energy seems to go down. So this is at least what we interpret from this data. So this is basically that the exciton becomes less of a rigid particle, and the electrons are basically screening the interaction strength. One has to say that for these samples, there is often at the moment sort of like a limit as to how much you can apply as a gate voltage. So how much you can dope. So how far you can push here before there is a sort of like before the insulator in between the two layers does not work anymore, and there will be just current flowing through the sample. So I think with like more experiments and with more experience on building these devices, one can probably push this limit more and basically see completely like that this exciton might at some point be not really bound anymore. But this is just a guess, I have to say. Yeah.
Which is the interaction between the electron and the exciton, or the interaction between two excitons?
So the interaction between the electron and the exciton is attractive. And
you have a form for that?
Yes, I think there is a form for that. As this is 2D experiments, so a 2D system, it's basically not just like a hydrogen atom, but I think it's a Keldysh potential that is relevant here. But then for the exciton, it depends on in which of the K values the exciton actually is. So here you see the calculation for the Brion zone of the band structure, and there are these K and K prime points where basically for graphene there would be this level crossing that has the direct cones. Now for the TMDs there is this direct band gap, and it turns out that these points here are of two different types, and one can excite the specific excitons with different polarization of light. So one can address either the K or the K prime value. Now, if the two excitons are in the same value, their interaction is repulsive, whereas when they are in different K values, it is attractive, and there is then this bound state, this exciton, bi-exciton observed. And I have to say here that this energy is not completely clear yet. So from the experimental point of view, there were measurements that have seen 19 MeV, and there were other experiments on the same material that saw 11. So also from the experimental point of view, it's not completely resolved, like what the interaction really is. I think we're really at the starting point of learning about it. In this case, I think yes. Yeah.
But the electron and the exciton, no.
Yeah.
So
Yes, exactly. Yeah.
okay. More questions?
I had one over here. I was wondering, could you remind me the effective masses of the electron and hole in this system?
Mm-hmm. So for the the electron and the hole effective masses are almost the same, and they are 0.6 to 0.7 of the free electron mass. So it's quite heavy actually in these systems.
So this would be somewhat more similar to like the positronium negative ion as opposed to the H minus, for instance.
Okay, yeah, in that sense, that's true. I mean, there is not like a heavy object and a light object, but they are equally heavy, yes.
I was also wondering about your few body part where you deduced the density matrix.
Mm-hmm.
As I understood it, you had an adiabatic ramp that made the system, and it was then that system you measured the density matrix of it.
Exactly, yes.
So, but since it was an adiabatic evolution, couldn't you take that back and deduce the density matrix before the adiabatic ramp as well? Does that make sense? Right, because you have a Liouville equation for the density matrix.
Yeah.
And if this system with that density matrix was deduced by applying fields to another system,
I see.
couldn't
Okay,
you go backward to find the original time zero density matrix?
Okay, I mean, here one has to say, like, before we saw this, we knew already that we have this spin singlet, just for a similar reason that what one does in an experiment is one goes adiabatically to the state and then goes adiabatically back and looks at, do I really have the same starting situation then, like without the ramp back and forth. So that's how one basically tests that one really ended up in this state. So this is sort of like more of an academic question in the sense that, like, if I, for example, have now these coherences and I cannot distinguish the entries here and there, can I still, like, without having the complete information, can I still learn something about the entanglement? But I agree. So if one knows all the fields, one could, of course, now say, like, well, I could infer the final density matrix. But for the same reason, I could already say, well, I mean, I did know that what the situation is here.
Okay, Dorte?
Yeah, for the second part, I was wondering, would the concept of scattering lengths make sense at all for those systems, or is this just completely the wrong starting point for thinking about the description? I don't know, Georg, if you have any input. Yeah, so the question was for the second part, you know, just more generally to stimulate sort of connections between the different talks and systems.
Yeah. So
if we, you know, think about this, could we think about, you know, use as a starting point some scattering lengths to describe the system of some contact interaction? But I think
so I guess, I mean, first of all, we have the binding energies. Now the question would be, what is the potential, the scattering potential and then if the scattering potential is such and such, can one really get a single parameter that characterizes everything? So I don't know. I mean, I don't know the answer. I think probably Georg knows it much better than I do. But my first guess would be when the interaction is very complicated. I'm not sure whether it's so. is there like one number that is sufficient?
I think that at least, I'm not an expert in these interactions either, but you can get very far by assuming short range interactions between electrons and excitons, for instance. And then to model these systems, you calculate the two-body scattering matrix with a short range interaction. And that can bring, I mean, there are effects from the fact that the exciton is a two-body bound object. But as you said, in these materials, it has a large binding energy. So a lot of the technology you have from the short range interactions in cold atoms carry over. It's just 2D instead of 3D.
So you're saying the systems are weakly bound compared to the other scales in the problem?
Well, I'm saying that the exciton is strongly bound so that it looks like a neutral particle, as the electrons see a neutral particle. That's why it becomes a short range. But then, of course, you can make these bilayer excitons, which are dipole. Yeah, that's a different story. But in many of the theories, also you show some of the theories, they assume just short range physics, short point interactions.
Yeah.
We have a question by Neil.
I just wonder, because if this is dipole-dipole interaction, the long-range part of the interaction is clear. And to describe it, is one of R square interaction as short range is questionable. It really depends, however, on the orientation of these two excitons. If they are parallel, perpendicular, or anti-parallel, then you can get different situations. But in general, I would say that no, there's no short-range interaction. There can be short-range interaction on top of the dipole-dipole interaction.
There are two more. Short, please.
Yes, but are these excitons oriented in this kind of structures? Because if they are not polarized, let's say, if they are in the S state, right? Then of course S state, the interaction between two dipoles in S state is not 1/r², right? Only at short range. So I don't know I don't know about excitons. Are they polarized or they can be described as kind of S wave, each of them?
So basically, first of all, they are sort of like not polarized in the perpendicular, but they are lying in the plane. And then the question is really, are they in which configurations can they be? And as I said already, there is the repulsive ones for the same valley, and there is the attractive ones for the different values. So you can really think of it in this way. Yeah.
And the last, it's not anymore. Okay, so thank you again.